All right, so last time we left off with a couple of sorting algorithms. We covered selection sort and in full with a full implementation of that. And then we described quicksort, but we stopped short of actually implementing that because we're going to focus all the rest of our time on how to do this stuff in practice. It is rare that you actually write your own searching or sorting algorithms. Instead, you want to use what's built into the standard library. Remember that we are online, so if you have any questions, go ahead and post them to Piazza or to the YouTube live chat here. How do we do this stuff in practice? Again, generally you don't want to write your own sorting algorithm, because if you did, what you would do is you would cut and paste over and over and over again the same sorting algorithm, same code over and over again, and just replace how you are comparing two things. Remember that are these things out of order, and so we need to swap them, right? The thing that you do to keep this general is that you only write one sorting algorithm, and that's usually provided by the standard library, right? But a sorting algorithm doesn't know how to order things. A sorting algorithm knows how to sort things, right? If you told the sorting algorithm that these two things are out of order, okay, well, it's responsible for putting them in order. It's not responsible for ordering things, right? Given A and B, are they in order, are they out of order, or are they equal? That's where a comparator comes in, right? This thing that we plug into the sorting algorithm. So not only are we sorting an array as input here, but also as input, we're giving it this other component over here that's responsible for, given this A and B, do I need to swap them or not? Or with selection sort, when you're trying to find the minimum element, is this less than this, so that therefore this is the minimum element so far, right? Answering those kind of questions are passed off to this comparator function over here. And it has a very familiar pattern with what we've seen before with, say, strcmp. That given these two things, A and B, if A comes before B, A is strictly less than B, then it returns something negative. If they're equal, it will return 0. And if they're out of order, if A comes after B, right, it's strictly greater than B, then it returns something positive. Again, we've seen this pattern with strcmp. Strictly speaking, strcmp is not a comparator. We'll get into the technicalities here momentarily, though. Okay? But this pattern should be familiar. And let me tell you right now, this pattern is in every single programming language ever made and will ever be made, because it is such a simple fundamental pattern, right? If you've got Java, there's this comparator pattern. You build actual comparator objects, or you implement what's called a comparable interface. C++, C#, every single programming language I've ever seen, the first question you ask yourself is, how do you sort? Okay, well, there's this sorting algorithm over here. Okay, how do I pass in a comparator so that I don't have to rewrite that sorting algorithm over and over and over again, right? So get familiar with this pattern, because it is in every single language, period. Right? All right, so in general, again, we don't want to have to write our own sorting algorithms. Why? Because, well, it's a lot of work. Here, just a second. Let me get to where I wanted to be. Here we go. All right. It's lots of copy pasta for different types. It's lots of testing, right? Lots of debugging, right? We usually say don't roll your own, right? Don't roll your own sorting algorithms. Don't roll your own searching algorithms. This actually comes from cryptography. Don't roll your own crypto systems, right? Because there are lots of mathematicians who would be able to poke holes into any garage-built kind of crypto program or something. So we always say, don't roll your own. Well, we'd also say, don't roll your own when you've already got it in the standard library. Just use it, right? And we've saw that before. It's called qsort, right? What is qsort? What is that short for? What do you think? Quicksort, exactly. Now, it's not necessarily quicksort implementation. In fact, modern implementations are going to be some sort of a merge sort hybrid, or maybe even timsort. Don't worry about it. It's still going to be called quicksort, qsort, because that's what it was called 30, 40 years ago, whenever it was, right? And its other built-in algorithms, they know how to sort. They just don't know how to order, right? They don't know what elements are the sorting algorithm doesn't know what type of elements it is sorting, and therefore does not necessarily know how to order them. Ordering and sorting are different things. Ordering is just with two elements. Are they in order, out of order, or are they equal? Sorting is different, that you are rearranging multiple elements, okay? And so QSort needs to be told how to order those things, whatever those things are, right? Comparator function, right? I don't even know if that's a real English word, but my spell checker doesn't care about it, so it must be some real English word. Otherwise, it's just a colloquial term in programming or something, right? Comparator function solves this problem, right? And again, it's the same pattern that we've seen before, that you give it two elements, and it returns something negative if A comes before B, 0 if A conceptually equals B, and something positive if A comes after B, or comes, B comes before A. Now, note here that I have emphasized the word something. You cannot necessarily read anything into the magnitude of that number. In fact, when we implement our own comparators here, I'm simply going to return -1 and +1, all right? It doesn't matter if it's -42 or +101, right? What matters is that it's negative, positive, or 0, okay? Now, how is this going to work, right? It's really clear from the depiction here about how to import or how to input an array, right? We've done this over and over again now for the last month or so. But it's really not clear how we can input this function that takes two elements over here as input. In other words, I want to give this function to this other function over here, right? So that's what we're going to have to focus on first. And to do that, we're going to bring in our old friend pointers, right? But instead of pointing to data, they're going to point to functions, right? So again, how do we pass a function to another function? Doing so is generally referred to as a callback function, right? It allows the function that you give it to call it back, right? You see this some of the times in graphical user interface programming, right? Where you design a button, right? And what you do is you register a callback. When somebody clicks this button, call that function over there. Because you don't want to have to break open the code for that button and then insert the code that you want right in that button or whatever, right? Instead, you want to register and tell the system, the windowing system or the GUI system or whatever, when that button gets called, call that function over there. How do I register it? I have to get that function and I have to give that function off to another function as a callback, right? QSort also needs, QSort also needs a callback function, right? A function that allows it to order things, right? A and B, right? And so we're going to give it this function and call that function when you need to know whether or not these two things are in order, out of order, or they're equal, right? So how do we do this? How do we do this, right? So consider, what is stored in memory? What is stored in memory? What do we know of already that's stored in memory? Data, right? Data is stored in memory. For example, an integer, a double, right? Arrays of data are stored in memory. How can we refer to that integer over there in memory? What am I doing? I am pointing to it, right? What else is stored in memory? Files are stored in memory. How do we read a file? File star is a file pointer. It begins at the beginning of the file, and then as you read character by character or line by line, right, it advances that pointer to the next thing because the file is stored in memory, right? Well, what else is stored in memory? Programs. Programs are stored in memory, right? And what's one part of the program? Functions, right? So functions are stored in memory somewhere, right? As a result, it makes sense that to refer to the memory location of where a function is stored, right? And as a result, you can refer or point to that function in memory, okay? So let's go ahead and take a look at a demonstration of syntax here. And for that, I'm going to go back over to our IDE here. Okay? All right. Well, again, how do I create an integer pointer? Is that big enough for everybody in the back? Yeah, okay. Int star x, right? Or actually, I'll call it ptr to x, right? And I can make it point to an integer, x, if I make that, just assign that a value of 42. And I can make it point to it by getting its memory address of x, right? We've done this now a couple of times throughout the entire semester, okay? What I want to do is I want a pointer that points to a function. But what is a function? A function is a name, it's a return value, and then it's parameters, right? So to do that, I need a function pointer. So let's go ahead and create a function pointer that can point to a function that A, returns an integer, B, takes an int, a double, and a char as parameters, okay? And I need to give that pointer a name. Right here, this variable, what's that variable's name? X. That's its identifier. What's the pointer to x called? ptr to x. So what I'm going to do is I'm going to create a pointer, and I need to specify the pointer's name here. Here's the following syntax. There's the return value, int, okay? And then inside of parentheses, the parentheses are important because of order of operations. If I didn't have parentheses, I'd be like up here. It's a pointer to a variable of an integer. So I'm going to have parentheses here, and I'm going to call this ptr to func, right? It's short for function, right? And then I'm going to specify that it takes an int, a double, and a char. Right? There we go. And that's it. Right? That creates a pointer variable that can point to any function that returns an integer and takes 3 parameters, an integer, a double, and a character. Now, what is the name of that pointer? ptr to func, right? Okay. Well, right now, what is ptr to func pointing to right now? Well, answer the same question for the first pointer, because we've answered this now several times. What is ptr to x pointing to right now? Could be, right now, now that I deleted that thing, right? Just anything. Who knows, right? Same answer. Who knows what this is pointing to, right? So, who knows? Dead beef, or dead beef. There we go. And I'll emphasize that it's a hex code, dead beef, right? It could be pointing to something. It could be pointing to null. It could be pointing to a piece of code that does not belong to my program, but instead belongs to, say, the operating system's program, right? A piece of memory where an operating system program is running right now. Should I be able to access that memory? Nope. In fact, if I tried to, that would be an injection kind of attack where I could say, change the contents of that memory and change what the operating system will do next time it executes that code, right? You can do that, and it's very, very dangerous, and you try to protect against that when you write an operating system or other code. All right, so what is it? Let's make it point to null, just to be safe, so that it's not pointing to some random dead beef memory location.
Dead beef actually like something that it that is in memory, or is it just?
It's a joke kind of that some compiler writers will use as uninitialized memory. All right, it's hex speak. All right, so my go-to is going to be X, B, A, 5, E, B, A, 1, 1. Yay, good job. Great. You can read hex. There we go. So let's make it point to null. ptr to func is going to be null. All right. Okay. So let's make it point to an actual function. Actual function. ... How do I do that? Well, I need that function to begin with, first of all. So let's write a function, right? And I need a function to return an integer. I'll call it foo, right? Because this is just going to be a fake function. It takes an integer, x, a, double, b, and char c. Right? And who cares what this function does? Maybe it just prints everything out. Print A is equal to %D and the line, and then B is equal to %F, and C is equal to %C and the line. A, B, and C. Right? And maybe it returns, I don't know, 42. Okay? Now, how would I normally, here, let's go ahead and make sure that we can actually point to it. PTR to func is equal to, now how did I do it up here? Can I do it like that, which is saying pointer to x is equal to x? Nope, that makes it point to memory location 42, right? Which doesn't exist, or doesn't belong to me, or whatever, seg fault. So I need an ampersand in front of there. So how do I make pointer to func point to foo? One way is to do the exact same syntax. Foo. Right? Now note here, when you have a function, you usually see a function in the context of calling a function, right? Foo with the parentheses there, and then you pass it A, B, and C. That's not what I'm doing here. Foo is the function's name, just like x is the variable's name. And so it makes sense to talk about that function's name, and that's its memory address. Right? So if I put an ampersand in here, or shorter, you can just go ptr2func is equal to foo. Right? For the same reason that you can do this with arrays, right? When you pass an array, you don't need to put an ampersand in front of the array because the array name is already the memory address. A function's name is already the memory address of that function. Right? So either syntax is perfectly fine. Okay? Once I've got a pointer to a function, how could I use it? Well, I could call foo normally, and what I mean by that is x is equal to, what did I call it, foo? I need an integer, so I don't know, 101, 3.14, and C, capital C there, right? Again, all it's going to do is print stuff out. Right? Let's actually go ahead and compile this and see its results. There we go. There, 101, 3.14, and then C. Okay. Now, how could I call foo via its pointer? The exact same way. X is equal to ptr to func, and then pass in the same values, 3.14 and capital C. There we go. And we'll see when I compile this that it'll actually call that function twice. Exact same function, exact same results. Who cares? Why do you need two identifiers pointing to the same function so that, I mean, you can call, why do you need foo and why do you need pointer to func, right? Well, it's so that you can now solve the problem that we were trying to solve before, of how do I pass a function off to another function, right? So to understand that, let's write another function here, double run math, right? All right, the idea here is that this function, this function takes a math function, takes any math function, right, that takes a double and returns a double and runs it, right? Okay. On the given input. So in other words, on the given input here, I'm going to go ahead and go with double x, right? Oops, and I need to close my comment. There we go. Okay. I'm going to take a double x, and I'm also going to take a function, a math function. For example, square root. You give it a double, you get back a double, the square root. Sine, you give it a double, you get back a double, and whatever the sign is, in radians, right? So how do I pass any old math function to this other function here? By giving it a function pointer. Now what would the syntax for that be? I need to return a double, so there you go. And then I need the function's name, which is going to be, I don't know, f, right? And then it takes a double. There we go. Exact same as down, oh, I think I need a pointer though, right? Something like this. And I don't think I need these parentheses here. There we go. And to emphasize that it's a pointer. Let's see if this compiles. Hopefully it does. Yep, it does. I got my syntax correct. All right. Now, is f sine? Is it cosine? Is it square root? Is it tangent? Yes, it's all of those things. It's whatever you gave it, right? So let's go ahead and run it. Double y is equal to f of x. And we'll return y. Right? Now, if this were square root, of course you could just go square root, but then that means you could only ever call square root. If this were sine, then same story. You could only ever call sine. Right? But if I name it f, any old function, now I can pass this function in to one function and have it run multiple times. Right? So for example, down here, let's go ahead and do it. I will create a double star, actually no, I'll just directly call it, right? Double y is equal to run math, right? And I'll run it on 3.14159, right? And let's go ahead and call the square root function, right? And print the value, printf, %d in the line, or y is equal to, so that we know what it is, %f and the line y. There we go. So, oops, what did I need? The math library. There we go. Math.h. And then I need to compile it with math library. There we go. Okay. Now let's run it. What's the square root of 3.14159? We'll find out in a moment here. 1.7, that looks about right. Maybe, I don't know. I'm not going to do that in my head. Right? We can run math on the same variable here, but a different function. Sine. What's the sine of almost pi? 0? Nearly 0. And so the answer will be nearly 0 as well. Right? What? Give me another math function. Does pow take one double and return one double? Nope. So could we call pow here? Oops. Nope. I want terminal. Sorry. This is not going to compile, or it will compile with a warning probably, right? Yep, warning. Wait, no. Pow takes 2 arguments, but I took a pointer, a function pointer here with 1 argument. So it'll run, but I have no idea what it'll do. Probably ignore that second one. Yeah, and return 0, something like that. Right? So that's not going to work. Give me another one. Okay. Yeah, log, natural log of 3.14159. I'm not going to know that off my head. If I don't know what square root of pi is, I don't know what that is. But that looks close. Good enough. All right? Et cetera, et cetera, et cetera. Right? All I had to do was pass that function, pass that function, pass that function. Right? Now, again, why is this a good thing? Because it allows us to treat functions as inputs to other functions. Right? Think of one use case that you could do with this run math here. In years past, I would, if we assumed calculus, I would have, I would still assign this as an exercise, right? So think about think about an integral. Have you done integrals in calculus yet? Some of you may have, right? What's one method for doing an integral? Simpson's rules, Riemann sums, et cetera, right? So you could write a Riemann sum, right? But you only want to write one Riemann sum function, right? That you can apply to square root, that you can apply to x squared plus 5x minus 9, right? There are an infinite number of functions that you can write that you can then throw to this Riemann sum function, right? Instead of having to write a Riemann sum function for this function, and then a Riemann sum function for that function, and a Riemann sum function for the third function, et cetera, et cetera. You write one procedure because it's one algorithm that you can apply to any math function that you want, right? Pretty cool, huh?
That would have been nice a year ago.
Well, typically math classes are way behind in technology times. Like they don't want you to use tools like Wolfram Alpha or something because all you have to do is put it in and it solves it for you, right? In fact, there are nice tools out there that will not only solve it for you, but go step 1, step 2, step 3. And so you could just copy it over and you're done. In fact, even when I was a grad student, I used that. So I was taking a crypto, it was a networking course and there was a crypto course, and we had to do polynomial long division, which is just a bunch of grunt work. And so I did it on a piece of paper, and I thought, okay, well, now I need to type it up in LaTeX. And so I thought, well, there might be a package out there that helps me typeset it a little bit better. I go and find a package, and it actually did the work for you. And so I just typed in the 2 polynomials, and it cranked out the LaTeX for me. And I go, well, why did I do that in paper? Okay. But yes, that's exactly why computer scientists are better, because I don't want to solve this. I'll write a program and then let it solve it for me, and I'm done, right? Go home, right? On Reddit all the time you read about people with just a small, like the minimum amount of knowledge, getting into an area or discipline with 0 knowledge and getting away with absolute murder as far as productivity goes, right? Oh yeah, I'll go ahead and take that data entry job. I'll automate it. All I'm doing is entering crap into Excel all day. I'll go ahead and automate it with this script, and I'm working from home now, and I'll take a second data entry job and a third data entry job. I'll automate all of those, and now I'm done, right? So you read about that stuff all the time. That's why our discipline is so awesome, right? Because we can make all other disciplines obsolete. Maybe not, I don't know. All right, so there's the demonstration of the syntax. How do we go about using it, okay? So to do that, what we need is a comparator, right? And so let's talk about comparators. Sorting in C, ... Well, no ellipse, right? Comparators first. We need this thing right here, okay? This thing right here is a function, a comparator. A comparator function, it is a function with the following signature. Remember what signatures are? It's the return type, the name, and then the parameters. Right? I'm going to copy this over so I don't have to retype it. There we go. It returns an integer. CMP is just short for compare or comparator. Right? Const void star A and const void star B. It takes those 2 elements and it returns something positive, something negative, or 0, depending on the relative ordering of those things. We've already seen that pattern over and over again here now, right? But what about the other parts of it? Why const? It's making a promise, right? It's making Scout's honor, I am not going to make changes to this, right? The comparator will not and cannot make changes to the 2 input values, right? Okay, that's nice, because it's just going to compare them. Does it go like this, this, or this, right? And it's going to return a value, right? Both are void star variables. Where have we seen that pattern before? Void star. What returns a void star? What returns a pointer to a generic memory location? Malloc, right? Why does malloc return a generic void pointer?
Because you don't know like what type it's pointing to.
Right, it's just a chunk of memory, right? You don't know if that's pointing to a bunch of doubles, a bunch of integers, or characters, right? It just says, here you go, here's your memory, right? That's because we don't want a malloc for integers, a malloc for doubles, a malloc for chars, right? We just want one malloc. And so this is a generic void pointer, a generic void pointer, right? It can point to any type of anything. So how do we go about, another caveat here, if the function has any other signature, it is not a comparator. So remind me, what does man strcmp look like? Right? strcmp, to compare 2 strings. Const char star, is that technically a comparator? Nope. The char there disallows it from being an actual comparator, right? Now, there are ways that you can use a strcmp, and we will use them in all of our demonstrations here. Use this particular function, but technically, this is not a comparator, right? We're going to have to deal with that later. A comparator follows the same basic pattern. All of them do. All right. So a comparator follows the same basic pattern, right? One. First, it typecasts the two values, A and B, into the expected types. For example, if you're writing this comparator for integers, it will typecast them as integer pointers so that it can treat them as integers. If you are writing a comparator for airports, like you will be this Friday, or maybe in your hack, I forget which one it is, then you will typecast them as airports because that's the type that you expect, right? Then too, it makes a comparison between the state of the two variables, returning an integer value depending on the ordering, okay? So let's go ahead and take a look at a demonstration here. For that, let's go ahead and go back to the original sorting demo here that we were working on. Let's refresh this. There we go. Sorting demo that we were working on last week. Remember, we wrote this selection sort algorithm. We wrote this binary search algorithm, but it was all for integers, right? Now what we're going to do is we're going to change this so that we're not operating on just integers. Well, we'll initially operate on integers, but we'll see how we can use qsort here for any other types, okay? Here's a, where's utils here? There we go. And open this one too, right? Here's a preview of what a comparator looks like. I called this CMP int. Why did I call it CMP int? It's a comparator for integers, right? So this function, this is a comparator function for integers, right? That orders them in ascending or descending order. I don't know. Let's find out. How did I write this? All right, now how do you know that this is in fact a comparator? What's the return type? Integer. What are the two parameter variables here? Const void star, const void star. Does that conform with our definition? Yes. So this is indeed the signature of a comparator. Let's actually take a look at the implementation, okay? Take a look at that first line. What am I doing there? I'm creating a variable, an integer variable x and an integer variable y. And I'm typecasting A and B, and I'm getting their values. How does that work? Well, inside here, what I'm doing is I'm saying, A, you become a const int star, a pointer to an integer. Why? Because before it was just a pointer to a raw memory location, right? I don't know how many bytes that is. But as of this typecast right here, it's now pointing to a memory location of 4 bytes, which is going to be treated as an integer. Then what do I do immediately outside of that? I have this star here. What am I doing with that? It's a dereference. Get the value stored at that memory location as an integer, and then put it into the variable x. I do the same thing for y, but with b. Okay? All right. And then what I do the logic. If x is less than y, then I will return -1. If x is greater than y, I return +1. Otherwise, I return 0. All right? Now, with that understanding, let's forget about that. And let's write a new comparator for doubles. What would that look like? All right, so this is a comparator function for doubles that orders in ascending order. And so I will have a comparator, CMP int. First of all, is that an appropriate name? And can I use that name? Nope, I've already used that name. I polluted the namespace, right? CMP double, okay. And, oh, good. I like that. Ascending, ASC, or ascending, right? There we go. All right. And it'll take a double x and a double y. Is that a comparator? Nope, not according to that definition. Oh, okay, you must have meant to pass in pointers, right? Nope, that ain't enough for the definition. All right, well, you meant to make them const so that you can't change them, right? That's good enough. Is it good enough? Nope. The last piece of the puzzle is void and void. Only when you have this signature do you have a comparator. Okay? Now let's write it together. I'm over here in util C right now. Right? Now we can do this in a couple of steps here. And I wrote it kind of efficiently in the other one, and I collapsed a couple of lines down. Right? What I'm going to do is I'm going to go ahead and make sure that, that we're doing this in a step-by-step process. And I will go ahead and create two const double stars. Let me go ahead and I'll go A for this one. And const double star B. Right? Okay. And I want to make A point to X by making a cast. Const double star X and const double star X for Y. Now, the only change that I've made here is I've changed this void into a double for these two variables. Right? Now, what are the actual values stored in those memory locations? So double first is equal to A. Can I do that? What do I need to do to A to get the value stored in it? Dereference. And then double second, dereference B. There we go. All right, now I've got the value of the first variable and the value of the second variable, okay? Here's a trick that you should not use, and we'll understand why, right? Let's think about a couple of values here. What if one of them is 10, what if the first one is 10, and what if the second one is, say, 5, right? What if I took the difference, double diff, difference, is going to be, say, first minus second. In this case, what value will I have? 5. 5 is positive, right? They're out of order, right? If it's an ascending order, I need 5 and then 10, right? So they're out of order, I'm returning something positive. What if they had the different value, 5 and 10? Now what's the difference? 5 minus 10 is negative 5. Hey, that's negative. They're in order, right? 5, 10. Right? What if they are both 5? Then the difference is 0. Hey, that looks like a cool pattern to follow, right? Until you realize that, what is 5.5 minus 5? 0.5. And if I try to return it, what happens? 0.5 truncation, and I get 0. Is 5 and 5.5 the same thing? Nope. That's called the difference trick. Avoid it. Avoid it like the plague, right? Avoid the difference trick, right? It doesn't work on doubles, values, and it risks overflow, underflow with integers. Right? So don't do that. In fact, avoid all tricks. Just write clear code, right? So clear code in this case is going to be what? If the first is less than the second, what value should I return? They're in order, so 5, 10, that's ascending order. They're in order, so return something negative. Something negative. Again, it could be 42. Again, why are you using the trick there? That's weird, right? Else if first is equal to second, if they're equal, what should I return? 0. Except that there's another trick here, right? First and second. 1 divided by 3 times 3 should be equal to 1, right? That's in math. What about in code? 1 divided by 3 is going to be what? Remember, it's a finite representation. So it's going to be 0.33333333. At some point it ends, right? 4 or 2 or something like that. When you multiply that by 3, do you get 1 back? Nope, you get 0.9999999, right? Less than 1. So avoid all those equals by making that your last case, okay? If second is less than the first, then I'll return positive, else I'll return something 0. Something 0, 0. By the way, there is such thing as negative 0. Don't do it, because negative 0 is negative, and you don't want to do that, right? Right? I think. Don't quote me on that. Anyway, again, avoid tricks. So make sure that your equality is always the last case that you check. Otherwise, write clear, concise code like this, right? And again, if you want to, you can go ahead and collapse those first 4 lines down into just 2 lines by making the cast and the dereference with 1 line. Okay? Okay. Cool. So now let's come back up here and reason through our CMP and answer that question that I asked before. Is it in ascending order or is it in descending order? So if x, which is a typecast of A, comes before y, we return something negative. So 5, 10, are they in order? According to this, yeah. So is this ascending or descending? Ascending. And take away that question mark. What if I wanted descending? I want you to sort, but I don't want you to sort in ascending order. I want you to sort in descending order. You do not write another quicksort algorithm. You write another comparator. Copy, paste. Can I use the same name though? Nope. Desk. Is that clear what I'm doing there? Descending, right? Descending order. Now let's write it. I'm going to go ahead and steal this code. There we go. Call it desk, right? And what do I do now? I could change this so that it's y is greater than x and x is less than y. There we go. That's a nice change, but that's still a lot of repeated code, isn't it? So how could I make reuse of some of this code? Another change that I could have done is what? I could have changed it so that it's not -1, but it's just negative. I flip -1 and +1. Right? Do I need to do anything to 0? No. Okay. Well, that code looks mighty familiar to that code. It's just switched around. Don't repeat yourself. DRY principle. What if I were to call that other function? Let's go ahead and get that result. Int result is equal to A and B. Return what now? So that result is going to be ascending, so it'll be negative, positive, or 0. If you want it to be in descending, what do you need to do? Just swap those around. So return a negative result. What happens to a negative value when you negate it? It becomes positive. What happens to a positive value when you negate it? It becomes negative. What happens to 0 when you negate it? It stays 0. Right? Okay, cool. Let's play some code golf now. How could I get that down in fewer in characters? Code golf, have you ever heard of that before? I can do that in 5 lines of code. I can do that in 2 lines of code. I can do that in 1 line of code and 10 characters. I can do that in 1 line of code and 5 characters or something, right? You get it down to as little code as possible. That's not a good way of doing things in practice, by the way. Don't do that in practice. It's just a little game. Right? But in this case, it's perfectly fine. I don't need a variable. I can return whatever negative that function call is. Yeah?
If we do it not, would you just flip it?
Okay. You could do that with 1 fewer character. I could do that with 1 fewer character. White space doesn't count in code golf. Oh, not C, A. There we go. Excellent. Right? So if you want a reversed comparator, all you have to do is call the original comparator with A and B reversed. Right? Excellent. So if I wanted a descending double comparator, don't cut and paste, just call it and reverse them. Now let's come back over here and actually use it. In fact, we've already used it. Right? We demonstrated this last time. But now let's go ahead and go into a more detailed use of QSort. QSort. There we go. So C provides a standard quicksort implementation. Again, it's not necessarily actually quicksort, and it's certainly probably not a recursive version of quicksort, because recursion is expensive and dangerous, et cetera, et cetera, et cetera. So it probably simulates the recursion instead. Right? There is the signature for that function. Let's walk through each one of those things. First of all, tell me about base. Right? Is this an array of integers? Is this an array of doubles? Is this an array of characters? Nope. It's an array of stuff, right? One function to rule them all. This is the array of stuff, right? It is generic. It's a void pointer, right? It does not have the const keyword. Why? Because you're going to be making changes to it. What changes are you going to be making to your array? You're going to be rearranging it so that it is sorted, right? If it's const and you're not going to be making changes to it, can you sort it? Nope. You'd have to make a copy, sort that copy, and then return the copy or something. Right? NEL. NEL is the number of elements, right? The size of the array. There we go. So that's pretty straightforward. Right? What about size itself? That's not the size of the array. That's the number of bytes each element takes. Now, why would it need to know that? They're integers. Therefore, they're 4 bytes. These two integers are out of order. I need to swap them. How many bytes do you need to swap? 4. Now it's an array of doubles. 8 bytes over here, 8 bytes over here. Now it needs to know that so that it takes these 8 bytes and puts them over here, takes these 8 bytes and puts them over here. Right? It needs to know how many bytes to swap when it needs to swap an element. Okay? And finally, or use the size of macro. Like you've been doing this entire time. Whenever you call whenever you call malloc, right? You use size of to tell it how many bytes you want. Right? And finally, compare, right? This is a function pointer to the comparator you want to use. Right? And what does that look like? Let's come back up here. It returns an integer. It is indeed a function pointer, star compare, right? And what does it take? 2 const void stars. Exactly what the definition of our comparator is. All right? Let's go ahead and use it on a small example. I'll go ahead and get rid of that too. All right, there we go. And bring this down here. I will want this array. And how big is that array? How many things are in their array? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go, 9. And so I will pass in the array, pass in the size of the array, the number of elements in the array, pass in size of int, and pass in CMP int. Remember that comparator is going to sort it in ascending order. So that when I print this out, we'll see that this old array here that's not sorted will now be sorted. So GCC sorting demo, there we go. GCC sorting demo along with utils.c, there we go. There. 0, 2, 4, 4, 9, 12, 34, 42, 102. Looks like it's sorted to me. How do we sort it in descending order instead? Remember that descending comparator that I gave it, or that I wrote? There we go. Does that look like it's descending to you? Yeah. What if I screw up big time? and pass it in a comparator for doubles, but I gave it an array of integers. Well, let's find out. First of all, it's going to complain. Oh, wait, no, what was it called? Oh, ascending, there we go. There. Now it'll be happy, but of course I will not get the results I want. Certainly that's not the same anymore, but is that what, is that sorted in ascending or descending any order at all? No, why? This comparator was treating those integers as doubles. So it saw that 4 bytes, but also the other 4 bytes of the next integer, treated that as a floating point number, and then made its comparisons. If you give it a comparator for some type that is not the array type, you're going to have undefined behavior, random garbage, right? You could have a seg fault. For example, what if I said double here, and we'll go ahead and go back to that comparator for integers, right? It's going to start swapping around 8 bytes, 8 bytes, 8 bytes, instead of 4 bytes, 4 bytes, 4 bytes. Let's find out what that looks like. There. Stack smashing event. Right? And that's only because this is part of the stack. It was statically declared. If it were a dynamically created array, we could do that by creating a random array of size 9. This will not be a stack smashing event. It could be that it just goes by with garbage results, or that it's an actual seg fault. Oh, thank God it's a seg fault, right? Or a corrupted top size here, right? That it was not able to do that because you were swapping around 8 bytes when each element was actually only 4 bytes. So you probably went beyond the size of the array into a place that you don't belong, right? Okay, so make sure that everything matches. Now this is a random array, so I don't know what it's gonna look like, but certainly it's going to be in order, right? In order, over and over and over and over again. Oh, wow. Why did I get the exact same result from 2 runs there? Because I was just that quick. Right? How are we doing random number generation? We're just seeding it with the time. The time was not as accurate, and so they ended up with the same seed, and we had the same result. Different result, as long as I go slower, slower, slower. But if I went there, wow. It's probably only accurate to a second or something like that. I don't know. I got the same 4 in a row. Okay. All right. Well, if we've got a built-in quicksort, must we have other sorting algorithms and searching algorithms? Well, first of all, quicksort is all you need. You sort it in ascending order, descending order, whatever you want, however you want. That's a comparator. There's only one sorting algorithm. But we did look at 2 different searching algorithms. What was one of those searching algorithms that we looked at? Searching. NC. There we go. What's one sorting algorithm that we looked at? What's the bad one? Where you had to possibly go through the entire array and get down to the end to say that it wasn't there. Oh, we don't remember? Well, it's just a for loop, yeah. And we gave it a name. Why? You check each element, right? And it was called linear search. Why is it called linear search? Because it takes a linear amount of time, right? If you've got 1,000,000 elements and what you're searching for ain't in there, you have to do 1,000,000 comparisons to find that out, right? So is there a linear search algorithm in C? Yes. It is called, darn it, man, L search. There it is. L search and L find, right? L search, L find. Let's go ahead. There is a different behavior here. I don't want L search. I want L find. Go back up. There we go. Let's focus on L find. There it is. And by the way, where is this located? Not in the standard library, in the search library. Right? So let's take a look at a standard, or the search.h library has a lfind and lsearch functions, has those two functions. We're only going to focus on the first one here. I will mention what the difference between them is, though. Let's align you up. Align, align, align. And there. Does that look better? There we go. All right. So it returns a void star. I wonder what that is. But otherwise, how is it different from QSearch here? Let me go ahead and syntax highlight it. So QSort, excuse me, is void star base, nel, size, and compare. Void star base, but now it's const. Why would the array now be const? You're not making changes to it, you're just searching through it now. You're not sorting it. nmemb is the same, number of members. Size is the number of bytes each element takes. And a comparator to say that, is this it, is this it, is this it? And finally it says, yes, that's it. How? By returning 0. Your key and this element match, right? There's the key element. It is one element of that type. What does it return here, though? It returns a pointer to the location that it found it. Okay? So let's go ahead and try it out here. Now, to demonstrate this, I do want to go back to our unsorted array right here. Let me go ahead and get rid of this. There. Right? And I'll print it out just to make sure that it works. Right? Now let's use lfind to find, say, 42. Right? Dot, dot, dot. Right? I need an integer, the key value, and I'll set it equal to 42. And I will have an int star result, and I'll call lfind, right? Mr. Find. Right? Lfind on the key, and then the exact same parameters that I used up here with quicksort, but I'm not actually calling quicksort now. Now, can I do that? Is the key the proper value there? What is key? On a regular old integer. What does lfind expect? A pointer, right? Not an integer pointer, but I can go ahead and get a pointer, and then it becomes generic by virtue of when it gets passed into that function. Okay. What happens when it's unsuccessful, do you think? Now, it will be successful here because it will find 42, right? So printf, found key value at memory address %p, end line. Right? And so I'll key and result here. So this will be a successful search. Why? Lfind, sorry, what do I need to bring in? The search library. There we go. Yeah. That's just a warning. Don't worry about that. Yeah, don't worry about that. All right, a.out. There we go. Ah, come on, really? You're going to be that pedantic about it? No. Why, whoa, that is something different. Why do you want a pointer to the number of members? Oh, lfind, lsearch. Let's go ahead and read the documentation a little bit closer here. And lfind. I know why you need it. Yep, you need it on both. Performs a linear search for the key in the array base, which has the number of elements of size bytes each. The comparison function referenced by compare is expected to have 2 arguments which point to the key value, blah, 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 in that order, in which case 0 is returned. Now, the difference here is lsearch. If it does not find a matching element, it adds it to the array at the end, right? lfind shouldn't be doing that, and so it shouldn't care that this is an actual pointer, but it is, for whatever reason. All right, fine. We will conform. There you go. I don't think that that's necessarily correct, but whatever, right? Yeah. All right. So size t size n, right, is equal to 9. It's going to be really pedantic about this. Don't worry, we're going to use B search, which is better. There we go. Finally, I got rid of the warnings. Right? Found 42 at memory address, blah, 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 blah. Right? Now, what happens when I try to find something that doesn't exist? Say 200. Do you see 200 in that array? Nope. What's it going to end up returning? What can it return, since its return type is a pointer, to indicate a special flag value of I did not find that? Null. There it is. And it's being printed as nil, which is null. Right? Nope, the first one. Right? It'll start at the beginning. Is that it? Is that it? Is that it? Is that it? Right? For example, I could put in 2 42s here, but it would still return the first one. Right? And to distinguish between those, I would need to actually print out the memory address of array here. And I don't want to go that far. Right? Now again, the difference between lfind and lsearch is that lsearch will, if it doesn't find it, it'll put it at the end, right? And cross your fingers that there's room enough to hold it, right? So you have to be very, very, very careful with lsearch. So those are the linear search implementations. What's the other one? What's the other kind of search that we've covered? Binary search. Right? That's the better one anyway. I think it's actually so good that it's not even in the search library. It's in the, oh, come on, there you go. It's been upgraded to the standard library, right? It's so important, just like QSort's in the standard library, bsearch is also in the standard library, right? Those other two linear searches, why would you want those? Well, for different patterns. They're not as common. So we'll relegate those to a special search library that you have to bring in. Right? But otherwise, these are so important, they're part of the standard library, okay? And it looks something like this. And again, I'll bring this over to the notes. The standard library has a binary search implementation. And the code for that, or the signature for that, is going to look, again, very much like QSort. Let me go ahead and line everything up here. It's going to take a key. It's going to take the array of elements. And here, it's much more sensible. It's not taking a pointer to nmem, right? That's much better. Otherwise, these 4 elements are exactly the same as QSort. The only thing that you need to do is pass in a pointer to a key, and then grab the return value here, okay? So let's go ahead and get rid of this stuff. And let's go back to 42 here. Right? And let's go ahead and go with the result. And instead, I will call bsearch. Now, bsearch will be exactly the same as QSort. Oops. But I'm also passing in the key as the first argument. Key. Except, what do I need to do to it? Get its memory address, because it's a pointer. Let's see if this works. There we go. What? Printf. Oh, there we go. Fine. All right. So now, 42 is in there, right? It's the first element. So should we find it? It returned null, an unsuccessful search. Why? For bsearch, for binary search to work, what condition needs to be met? It needs to be sorted. Is that sorted? Nope. Is it sorted now? Yep. So, fixed. It found it at that memory location. Is it sorted now? Yes. But is it sorted in the exact same way as binary search is expecting it to be sorted? No. So, once again, it will not have a successful search. 42 ends up being on the other side. It starts recursing and going down that direction, right? So the takeaway here is, if you are going to use bsearch, you need to have called quicksort on the exact same comparator. If I change both of them to the descending comparator, oops, no, I do not. GCC, there we go. Otherwise, I would have wiped away all my changes there. There we go. If they're both descending, then it will work again. So the takeaway is, if you're going to do bsearch, great, do it. But you need to first sort it by calling qsort. And it needs to be on the same types, the same array, the exact same comparator. Right? Otherwise, you might even get seg faults or something. Right? For example, if I did a CMP double ascending, I'm going to get seg faults on this probably. Oh, nope, just an unsuccessful search. Unsuccessful. Right. So CMP int disk. All right, questions so far? All right, then, what happens when we expand this idea out to, say, structures? Right, did we have, here, here's our faculty structure that we did a while ago, right? Where you can order, say, a faculty member by their last name, comma, first name, ascending or descending, so that Zermello is up here and Avery is down here, right? Or Avery is up here and Zermello is down here. Two different orderings just based on the name alone. Maybe you can order them by their NUIDs. Lesser NUIDs, and then in ascending order or in descending order, so that 99999 is up here and 00000 is down here. Or you can order them by their height in meters, ascending, descending. Or you could order them by their hire date. And if 3 or 4 people were hired on the same date, how do you break those ties? Go to their NUID, or go to their first name or last name or something like that, right? Generally, what you want what's called a total order. I don't know if you've had any discrete math yet, but have you ever seen a post set or a partially ordered set? No? If not, that's fine. Generally, what you want is a total ordering in your comparators, though. In other words, you don't want ties. If you've got a tie, then you've got a problem. So generally, to break ties, you go to something that is definitely guaranteed to be unique, like a NUID. They could have the same hire date, the same height, the same first name and last name. We hired 2 Herbert Detlofs on the same day, and they're exactly the same height for some reason. Like they're absolute clones, but we need to distinguish them somehow. One gets one NUID, another one gets a different NUID. Now they're orderable. We can say that this one comes first and this one comes second. Right? Again, pick it on him because he's the only faculty member I know here. Well, 2, I guess. Right. All right. Any questions? Nope. All right, then. We will go ahead and continue there next time.